second session of the Meet the Fellows event. And this session, we'll have 4 talks taking us through a tour through learning, proofs, cryptography, and so on. And the first talk is by Marco Carmosino, who will tell us about learning versus proofs of complexity lower bounds.
Hi, everyone. Thank you for the introduction. I'm Marco Carmosino. I'm delighted to be here. I'm a research scientist at IBM, and I'll be talking today about joint work with many people, including Antonine and Valentine, who are here. Okay, so the central conceit of this work is that simple concept classes should be efficiently learnable. So if you have a concept out in the world that's low in some complexity measure, should be able to teach it to students, right? This is of great concern to all of us. We have to define the terms from that slide. So let's talk about defining learning, okay? So curly C is going to be a class of Boolean functions. I'm going to define a very relaxed version of Valiant's PAC model from 1984. What I give you is I give you query access to any function in the concept class, right? So you can ask me for particular examples. You control the questions you ask. I give you random bits so you can toss coins. I think the last 3 talks have told us how important those are. So those are useful for the learner to have. And I give you non-trivial time, right? What I mean by that is if we have Boolean functions on n bits, I measure the amount of time and resources you take in the size of these examples, okay? And what I want from you is I would like you to output a circuit H, a hypothesis approximating the function f, such that the probability if we sample some new example x from the uniform distribution on bits, that your hypothesis agrees with the true function is at least 1 minus epsilon. It's good. So you have good agreement with the concept. Let me give a deliberately provocative example of a concept class and a particular concept. So first, let's start with the concept class being p-poly. That's general Boolean circuits of polynomial size and or not gates. The only thing I restrict is how many gates you have. Yeah. And the function from n bits to 0, 1 is this kitten function, where if I have one input, x1 over here is this kitten, one input, x2 over here, which is this dog of kings, this says yes, and this says no, okay? And I want to emphasize that I'm not lying to you about the function being Boolean. These are dithered images that are all completely yes or completely no pixels. Okay. So I told you what learning is. Now, what is simplicity? It turns out it's very complicated to define simplicity. We're not going to define it with bounded VC dimension, by the way, as in the talk earlier today, which was very exciting because that is a combinatorial parameter about the capacity of the concept class, right? That'll determine sample complexity for PAC learning. Remember, we're bounding your coins and we're bounding your time here. We care deeply about the computational resources, not just the sample and statistical resources. So I'm going to tell you that curly C is simple if we can prove complexity lower bounds against curly C without working too hard. Here's an example, AC0, so that's constant depth and or not gate circuits of polynomial size. That's simple. It can't even compute parity on n bits, and there's a constructive proof of that. Great. So this is maybe a somewhat complicated definition of simple now, right? Because I've just sort of moved the work. I've moved the work from the concept class is simple to saying that we prove it without working so hard. So now I have to define proof complexity. I'm not going to do that at all in this talk, but I'm very excited. But I'm very excited about those questions. Yeah, no, I have to define that too. That's the only thing I'm going to define. Right? No, yeah. A simple proof is kind of, I know it when I see it and I can extract a constructive proof from it. So that's the next slide. Thank you for the question. So here's our class of Boolean functions. Here's an associated meta-complexity problem. I want to distinguish C compressible concepts from randomness. I want to be able to tell the difference. So given the truth table of a Boolean function, that's a weird representation, right? This is like the MSSP problem. You're given the most explicit version of the function possible. I say no if that function is in the concept class, and I say yes to at least 1/5 of all n input Boolean functions. So I have sort of a randomness detector or a non-simplicity detector. The natural proofs paper of Razborov-Rudich says that constructive, again, that's in quotation marks because I'm not going to define it at all, proofs of complexity lower bounds give us efficient C distinguishers. They give us efficient algorithmic solutions to this problem. And this is a quote from that paper that I love, that I'm going to read out to you, even though it's on my slides. As long as we use natural proofs, we have to cope with a duality. Any lower bound proof must implicitly argue a proportionately strong upper bound. And what I like to do is turn those upper bounds into learning algorithms. Yeah, so this is what I want to be able to say. This is what I'm excited about doing at this program and more broadly in my life. I'd like to reduce learning to meta complexity problems. So if somebody comes to me and says, I have a learning setting, I say, great, okay, go prove this particular circuit lower bound in this nice proof system, and then you'll have a learning algorithm. This actually works. This class, AC0 mod P, which is, remember how AC0 was too weak to compute parity, we throw in parity gates and we get a stronger class. This is learnable over the uniform distribution with membership queries in quasi-polynomial time. That's joint work with Russell and Pagliazzo, Antonina, and Valentin. That's CCC 2016. And that's exactly the model on the first slide that I showed you. These next two are slightly better models, right? In this second result, we can unrelax the model a little bit such that the teacher might lie to you. They might adversarially corrupt some fraction of your membership queries. In this third result, which I should be talking about in one of our workshops, this is joint work with Antonina, Eric Benedict, Rami Ramya, and Manuel Sabin. We show that this class is learnable over any succinctly described product distribution. This is just a slightly more natural distribution than the uniform distribution over all pixels. And there's a somewhat generic pattern here, right? If we have a natural property against a complexity class, we get a learning algorithm for that class. What's nice about this is that the runtime and the noise tolerance, they depend on the quality of the lower bound in a very natural way, right? So if you can show that a certain function requires huge circuits, you get a very fast learning algorithm, which is great. And it's only somewhat generic because this pattern holds for any complexity class that contains AC0 mod P. And that's unfortunate. More about that on the open problems slide. So this is room for improvement. Okay, I'm not going to tell you anything about the proof techniques, except I'm going to show you this picture. We abuse the Nissan-Wigderson PRG in the reverse direction. And a nice idea from that is just a hybrid argument. We pick two endpoints, two different distributions. This is a picture of a kitten, and this is randomly sampled pixels. But it's not really randomly sampled because I got it from a website called randompngs.com. So they're probably using some kind of cheap pseudo randomness. We interpolate between these two, and we find a place where we get a sharp threshold between seeing a kitten and seeing randomness. This is just a nice picture of what a hybrid argument can look like. It comes up in these proofs constantly. There are many, many open problems in this setting. So first is that lacuna that I pointed out on the previous slide. Can we get generic learning from natural proofs below AC0 mod P? So can we get this technique to work smoothly for AC0? We can just automatically generate a learning algorithm from the natural proof instead of having to appeal to the proof against AC0 with parity. That would be really nice. That would be a tighter characterization. Can we learn from random samples in this model? Can we turn natural properties into learning from random samples for weak concept classes? This is related to the question of, do there exist weak PRFs in AC0 mod P? Following this really nice work of, and wonderfully named, conspiracies between learning and algorithms of Oliveri and Santanum, can we get uniform learning dichotomies where a concept class is learnable if and only if it doesn't contain certain kinds of pseudo-random objects in it, and it's learnable by an algorithm, not a circuit? That would be really nice. I'd love to work on that. Can we get better lossless compression? That's kind of a search to decision version of MCSP, where you instead of asking questions, you just get the whole function, and you need to give me now a perfect circuit for it, right? There are much better lossless compression algorithms for AC0 mod P than you can get by just running our algorithm, then filling in the errors in the truth table. But you can't get them generically from proofs of the lower bounds. I'd like to be able, so in Valentine's talk in the boot camp, he said, we do this kind of boosting where first we start with a weak learner and then we improve its accuracy using a construction that's like boosting. That construction comes from coding theory. It's like error correcting codes. It would be really nice if we could use standard boosting algorithms from the learning world on our learning algorithms in this setting. And yeah, it would be really nice if we could learn ACC0 non-trivially, somehow applying or extracting ideas from Ryan's breakthrough circuit lower bounds for that class. And finally, I'm really interested in improving the learning setting nuance. That's just saying, if there are new and exciting learning classes, I want to try and reduce them to interesting meta complexity problems. And that's pretty much all I have for today. Thank you.
Certainly have time for questions.
Lossless compression. So is that a better lossless compression for ACC0B? Like, what's that?
I believe
Maybe repeat the question in case.
Oh, what is the better lossless compression that is not generic? I believe Shrikant Srinivasan has an algorithm that compresses to sub-exponential, like it actually achieves the lower bound. But again, that algorithm, while great, directly inspects by a human the proof of the lower bound and then extracts a clever algorithmic idea. I want a machine that automatically turns the lower bound into a lossless compression algorithm with the same parameters.
Is it possible to say a little bit more about how learning from random samples is related to weak PRFs?
There's the paper of currents. So weak PRFs, right? The queries that you get to them are random. You don't have control over your examples anymore, right? So there you go. It's the natural model. And like I've been thinking a lot more about crypto recently, and here I want to be talking to cryptography people and learning how to flip the story between the cryptography primitive and the learning primitive. And I hope that we can obtain tighter and tighter connections this way between both disciplines. So yeah.
You have a question? Maybe a follow-up to the lossless compression question. Is that related to improper learning in some way? Because you allow to.
Oh, I didn't mention this at all. Okay. Wow. Okay. Sorry. Our algorithms, one of the parameters that depends in a very natural way on the proof is when you extract a distinguisher from a proof of a lower bound, that distinguisher has a computational complexity that is proportional to the proof system that it was proved in. And when you spit out our hypothesis, it embeds that distinguisher. So that's often in a different complexity class. Like if you just look at our algorithm, it learns AC0 mod P into like NC2 because we need to compute the rank of a matrix in a naive way. Yeah, so
it is improper.
Yes, it's improper right now, and it would be great if we could reduce the complexity of the proof such that we end up automatically with proper learning algorithms, but I don't even know if that's possible. In fact, we thought about this a while ago for AC0, and it seemed actually difficult to get proper learning for that. So
that's. What do you mean by proof? Just this was in your paper from 2016. You see NC2. You mean informal proofs, or?
Yes, I mean an informal proof. Although if you talk to Yan and look at the paper before the natural proofs paper, that notion can be formalized. But here we're just talking about, okay, if you can extract this particular type of algorithm from the proof, that's an I know it when I see it. It modularizes extracting algorithmic ideas from proof. You extract just this one algorithmic idea, and then you reduce learning to it. But of course, you can be more formal, and I would love to do that while I'm here.
Great. Let's take other questions, if any, offline. Thanks again.